Until now, we have only discussed black holes that are either in a binary star system or located at the center of a galaxy. Surely, those aren't the only ways to find black holes. Indeed, scientists think that there are isolated black holes lurking within our galaxy. So, how do we detect them? We need to remember the presence of gas between stars, called the interstellar medium. If an isolated black hole travels through a gas cloud, we would expect to see some of the gas to accrete onto the black hole. The accreting gas should emit X-rays, which could potentially be detected. Although astronomers detect lots of X-rays emitted from gas clouds, conclusive evidence for isolated black holes using this method hasn't been detected. If there isn't light being generated by an isolated black hole, is it still possible to detect them? Of course. Black holes change the gravitational field in their local environment, so light passing by is influenced by the gravitational field. Since black holes can strongly warp space-time, they cause light to travel on curved paths. We see the light from behind the black hole as being warped by gravity. This is called gravitational lensing. Here is a computer-generated starscape showing the constellation of Orion, along with the bright stars Procyon and Sirius. Brighter stars are represented by larger circles, and dimmer stars by smaller circles. Light can't escape if it enters the black hole's event horizon. So if a black hole were to get in the way of our view of Orion, we might see something like this computer-generated image, with a dark circular region where we see no stars. The black circle corresponds to the event horizon of the black hole. The black hole is blocking our view in the same way a cat blocks your view when it decides it's time for attention. But if we look carefully at the area around the dark region, it looks as though many more stars have appeared around its outer edge. The strange appearance of these additional stars is an optical illusion. What we are actually seeing is multiple images of the stars that reside in the background. For instance, you should be able to see 2 images of the group of 3 belt stars on either side of the black hole. Similarly, you can see 2 images of the very bright star called Sirius. What we would see is more complicated than just a black circle in the sky. Instead, light from the faraway stars curves around the black hole and arrives in our eyes as though the star is located at many locations. The black hole's gravity distorts the image of the background stars, giving away its presence. In reality, there is no black hole close enough to give us a view like this distorted picture of Orion. But we can use the concept of gravitational lensing to identify some isolated black holes. If this lensing effect is difficult to wrap your head around, you probably feel like a photon that's been bent in the space-time around a black hole. Let's have a look at a real-world example of image distortion by your dining room glasses. Stemmed glassware are simple vessels that can be filled with a liquid. Since an empty glass has curved edges, it bends and warps light just like a lens. When the glass passes in front of a picture, like this star map, a distorted view of the background becomes visible. Since the curvature of the glass allows multiple images of the same object, we see multiple images of some stars. Depending on where the stars are, they can also be distorted into rings. When gravity is weak, light travels along paths that we consider straight. Since gravity can distort space-time, photons are forced to travel along geodesics, which are curved paths that bend around the black hole. To us, the resulting images have multiple views of the same object, along with great arcs of refracted lights, similar to what we saw in the glasses. For this reason, when the gravity of a massive object curves the path of light, we call the massive object a gravitational lens. A gravitational lens can be a star like our sun, a galaxy, or a black hole. The more massive, the better. When the faraway object, the nearby mass, and the Earth have perfect alignment, the image that we see is called an Einstein ring. This diagram demonstrates the perfect alignment between the Earth, a nearby galaxy, and a faraway star. Light from the star can be emitted on paths that go around the galaxy and reach the Earth in many different ways. The light can go over, or under, or beside the galaxy. The result is that the light in our telescope from the distant star looks like it comes from a ring in the sky that surrounds the nearby galaxy. Here is an example of an Einstein ring captured in a photo taken by the Hubble Space Telescope. The fuzzy orange blob in the center of the picture is a nearby galaxy. The blue circular halo is a distant galaxy lying behind the orange galaxy. The mass of the nearby orange galaxy warps space-time, and the light from the faraway blue galaxy appears like a ring due to the gravitational lensing effect. The ring is not a perfect circle due to the fact that the orange galaxy's mass is not located at one point. If the source of light and the lens mass do not line up perfectly, we see multiple copies of the same faraway galaxy. In this picture, we see 4 lights that are all images of the same faraway quasar that is behind the nearby galaxy. The nearby galaxy is the fuzzy light in the center of the 4 quasars. This is called an Einstein cross, since it resembles a cross. When astronomers view images of gravitational lensing, they can compute the mass contained in the nearby galaxy. In many cases, the mass calculated from gravitational lensing is larger than the mass inferred from looking at the bright stars. This is one method used to show the existence of dark matter in galaxies. Although black holes could be a type of dark matter, most dark matter is not made of black holes. The size of an Einstein ring is related to the mass of the nearby object. For the images that we've shown, the nearby mass is a galaxy, and galaxies have gigantic masses, larger than 100 billion suns. The large mass gives a large deflection and a bigger-looking Einstein ring. If the lens mass is small, where small means similar to the sun's mass, and the distance is far from us, then the size of the ring will be too small for a telescope to resolve. Instead of seeing a ring, the light from the faraway star will appear brighter. This situation is called gravitational microlensing. The mass causing the lensing could be a dim star, like a brown dwarf, or a black hole. Astronomers have been monitoring many stars in a nearby galaxy to look for the microlensing brightening effect due to an isolated black hole in our galaxy. If the black hole is traveling between the Earth and the faraway stars, then they will appear brighter while the black hole is in front of them. This gives us a view of a star that appears brighter for a short time period. Microlensing by black holes is very rare, but it is seen occasionally. This image shows a gravitational lensing event that occurred in 1996. The top panel shows a dim star on April 28th, and the bottom panel shows the same star on November 15th. The image on November 15th is brighter, and a further analysis showed that the star appears brighter because a black hole with a mass around 10 times larger than the sun passed by. Only a handful of black holes have been found this way, since this is a really rare event.